You remember that when you multiply a vector with a matrix, it produces two effects, that is a scaling of that vector and rotation. For example, if you multiply this vector, so if you multiply this vector by this matrix, then you know how to multiply it. This product is equal to, that is, this vector when multiplied by this matrix becomes this one. Multiplication has produced two effects, scaling and then rotation. However, for certain vectors, these matrices only produce one effect, that is scaling. That is, if we have again this matrix and multiply it by multiply this vector by this matrix, what do we get is 30, 40. That is 10 times the same vector. You have multiplied a vector by a matrix, and this matrix has only produced scaling in that vector. So this vector is called eigenvector. Eigenvector for that matrix. And the corresponding value with which this vector is scaled is called eigenvalue. So eigenvectors corresponding to a matrix are vectors which when multiplied by that matrix will only produce scaling in that vector, and the corresponding value, numerical value, scalar, is called the eigenvalue of that matrix. Eigen is a German word which means self or own. Eigen means own, myself, my own values of this matrix. And now a few more terminology. If you have a matrix A, if you multiply it by a vector and the resultant is only a scaling in that vector, then this vector is eigenvector and this value is the eigenvalue. And spectrum. What is spectrum of a matrix? Set of all eigenvalues is called spectrum. Spectral radius. Spectral radius is the largest of absolute value of all eigenvalues. That is called spectral radius of a matrix. Yes, please. Eigenvectors ka set. So the question is, if we have multiple eigenvectors, then are these eigenvectors linearly independent or dependent? So remember that if we have this vector x is an eigenvector of this matrix, then its scalar multiple, any scalar multiple, for example y, which is equal to c multiplied by x, this y will also be an eigenvector. So any scalar multiple of these eigenvectors will also be an eigenvector. So the question should be, how many eigenvectors, linearly independent eigenvectors, are there for a matrix, so that we shall address. So if you have an eigenvector, then its scalar multiple is also an eigenvector. For example, for the matrix that we considered earlier, this was an eigenvector, and this, for example, is also an eigenvector. If you multiply this vector by that matrix, it will also produce some scaling in that this vector without producing any rotation. So these two eigenvectors are linearly dependent. So eigenvectors can be linearly dependent as well as independent, that we shall talk about in more detail. Now next question is how to determine these eigenvalues and eigenvectors. So how to determine that? So how to find those eigenvalues and eigenvectors? The same equation can be rearranged to write it into this form. If I bring this term to the left hand side, rearrange equation, I get this expression. So you remember from our discussion on system of linear equations that solution to this system of equation, you were talking about this system of equation. Under what conditions non-trivial solution exists to this system of equation? So if this matrix is full rank, this is n by n matrix. If rank of this matrix is n, then there is unique solution, you know. And unique solution in that case is the trivial solution, that is x equal to 0. Non-trivial solution only exists if rank of this matrix is less than n. And rank of this matrix less than n means that determinant of this matrix is equal to 0. So for this system of equation, this is quite similar to that. Instead of A, matrix A, you have this thing. So for a non-trivial solution to exist, this determinant of A minus lambda I should be equal to 0. So from here we get, this is called characteristic determinant. If you expand this determinant, you will get a polynomial, and that polynomial is called characteristic polynomial. So here is a system of equation, you know, we have made a discussion on it. If rank of this matrix is equal to n, the number of unknowns and the size of this matrix, then there is a unique solution, we know that. And unique solution, that is obvious, x equal to 0 is a solution, that is the trivial solution. Non-trivial solution, when would it exist? So the non-trivial solution will exist if the rank of this matrix, if rank of this matrix A is less than n, then non-trivial solution exists. Rank less than n means determinant, means that determinant of matrix A is equal to 0. Why? If rank is less than n, why determinant is equal to 0? Yes, so it means that some rows or some columns in this matrix, if rank is less than n, so some of the column vectors will be linearly dependent upon each other. Linearly dependent means scalar multiple of this, for example, column can be obtained, this column can be obtained by scalar multiple of, for example, this column, right? So therefore two columns are similar and determinant of that matrix will be equal to 0. So rank less than n means determinant equal to 0. So here the only difference between this system of equation and here is that instead of matrix A, you have another matrix. So for a non-trivial solution to exist, this determinant should be equal to 0. This determinant is called characteristic determinant. If you expand this determinant, you will have a polynomial. That polynomial is called characteristic polynomial. And from the characteristic polynomial, you determine the eigenvalues. Let's demonstrate it with the help of some example. So we have this matrix A given by, and we want to determine the eigenvalues and eigenvectors corresponding to this matrix. So this matrix is A. To determine eigenvalues and eigenvectors, we first write the characteristic determinant. Characteristic determinant is A minus lambda I, determinant of this matrix, which is equal to this minus 5 lambda multiplied by identity matrix, and then subtracted from here is minus lambda to minus minus lambda, this determinant, and then you expand it, you get, and then you simply multiply the terms, and you get lambda square, and then you want to find lambda, so you know how to solve this equation. We can solve it in different ways. For example, we can split this term. So we have lambda equal to -1 and lambda equal to -6. These are two values of lambda for which this determinant will be equal to 0, and that is, these are two eigenvalues for this matrix. And then how to find the corresponding eigenvectors? Now we know how to solve system of equations. We shall substitute this value of lambda over here and solve the system of equations. For lambda equal to -1, this equation becomes a minus for lambda equal to -1, so we just omit the intermediate steps. We have a -5 plus 1, 2, 2, -2 plus 1, x equal to. So here is the equation. X is eigenvector. We have already found the eigenvalues. We want to find the corresponding eigenvectors. For that purpose, we have simply substituted this value over here, and then you know how to solve this system of equations. How do you solve this system of equations? Several ways. You, for example, reduce this matrix into echelon form and then find the solution. So this is the augmented matrix. Right hand side is 0, and the matrix, this matrix. And then by elementary operations, this equation, this matrix is row equivalent to. So what is solution? Infinitely many solutions. So among those infinitely many solutions, you find some linearly independent solutions. Here you get the equation -2 x1 plus x2 equal to 0. From here, x2 is equal to 2x1. So what is solution? Take any arbitrary value of x1, and that will give you the value of x2. Remember that there are infinitely many solutions. Among them, this is one solution. Any scalar multiple of this vector will also be an eigenvector corresponding to this eigenvalue lambda equal to -1. So this is a vector corresponding to this eigenvalue. That is, if we multiply this vector by this matrix, there will be only a scaling, and the scaling factor will be -1. You can verify it by multiplication of that matrix with this vector with that matrix. For that is, this matrix multiplied by this vector, what do we get? -5 plus 4, that is equal to -1. And what is second entry? 2 minus 4 is -2. That is, if we multiply this vector by this matrix, this there is a scaling, and that scaling factor is equal to -1. Yes, you will always get infinite, because this numerical value will make this thing 0, determinant of this thing equal to 0, that is rank of this matrix will be less than n. Rank of this less than unknowns means that infinitely many solutions. Among them, this is one solution. And similarly, corresponding to second eigenvalue, lambda equal to -6, you can also find the corresponding eigenvector. So here you have -6, and then you have this augmented matrix. This augmented matrix can be reduced into this form. Multiply this first row by 2 and -2 and add it with the second row, so you get 0, 0 over here, and corresponding eigenvector can also be determined. That is, it is obvious that the eigenvector corresponding to this eigenvalue will come out to be equal to, if we take this is x1 equal to -2x2, so if we take it equal to 1, then this is -2. So this eigenvector corresponding to this eigenvalue, the second eigenvector corresponding to second eigenvalue. So the procedure to determine eigenvalues and eigenvectors is quite simple. So the question is, these are two different questions. For example, first question is it an eigenvector of this matrix? The answer is yes. So is it an eigenvector to this matrix? The answer is yes. So similarly, any scalar multiple of this vector will also be eigenvector for this matrix corresponding to this eigenvalue. Similarly, this one -2, 1, this is an eigenvector. Another eigenvector is this one. This is another eigenvector, and there are infinitely many eigenvectors. So among them, these can be linearly dependent. Corresponding to this eigenvalue, we have an eigenvector. Corresponding to this eigenvalue, we have another eigenvector. These two eigenvectors are linearly independent. So determine eigenvalues and eigenvectors corresponding to this matrix. Please do it. So there is one eigenvalue at 5 and two eigenvalues at -3. So we say that this eigenvalue has algebraic multiplicity of 2. This eigenvalue has algebraic multiplicity of 2. So find the corresponding eigenvectors. Eigenvalues we have found, that is, find the solution to this system of equations. Corresponding to this eigenvalue, we have this system of equations which rewritten over here, and then you know the procedure. You will transform, you will write an augmented matrix, and then corresponding to that augmented matrix, you will perform elementary row operations to transform it into echelon form, and that echelon form, I hope you can do all these steps. So that echelon form is given by, so to solve this system of equation, you construct augmented matrix, that is, augment the right hand side of this equation, system of equations with this matrix, then perform elementary row operations to transform this augmented matrix into echelon form. Once we have echelon form, then the solution can be found. From the second row, we have 8x2, or even we can further simplify it to write 1 and 2. So here 1 and here 2. So x1 plus 2x2, that is equal to 0, which means that x1 equal to minus 2x2. From the first equation, first row, here is x2 and x3. Here is x2 and x3, and x1 plus 2x2, 2x2 is itself minus 2x3 plus 5x3, that is equal to 0, which implies that x1 is equal to minus 4 plus, so minus x3. And how many solutions are there? Infinitely many solutions. One solution is given by, if I take for example x3 equal to 1, then x2 is equal to minus 2 and x1 is equal to minus 1. So corresponding to this eigenvalue, we have found an eigenvector. Similarly, corresponding to second eigenvalue, we find an eigenvector. So we solve this system of equations. A plus 3i into x equal to 0. We solve this system of equations. You all know how to solve it. So what you will do, you will construct an augmented matrix by augmenting the right hand side of this system of equations with this matrix, and then perform elementary row operations to transform it into echelon form, and that echelon form is given by, from this system of equations, you constructed augmented matrix and then performed elementary row operations to transform it into echelon form, which is given over here. That is, you have x1 plus 2x2 minus 3x3, that is equal to 0, or x1 is equal to minus 2x2 plus 3x3. Again, there are infinitely many solutions. Among those solutions, you are interested in determining the linearly independent solutions. So how would you do that? So let's take, for example, x2 equal to 1 and x3 equal to 0. Then the solution vector is given by, if we take we have taken x2 equal to 1, x3 equal to 0, and therefore x1 is equal to minus 2. Similarly, if you take, for example, x2 equal to 0 and x3 equal to 1, that will generate this solution, x3 equal to, and then x1 equal to 3. So for this matrix, we had an eigenvalue lambda 1 equal to 5, another eigenvalue at minus 3. Algebraic multiplicity of this eigenvalue is 2. Corresponding to these eigenvalues, we have determined eigenvectors. Corresponding to this eigenvalue, there was a single eigenvector. Corresponding to this eigenvalue, we have 2 eigenvectors, and we say that geometric multiplicity of this eigenvalue is also 2. Geometric multiplicity is the number of eigenvectors associated with that eigenvalue. So how many eigenvectors are associated with this eigenvalue? 2 eigenvectors are associated with this eigenvalue. Therefore, geometric multiplicity of this eigenvalue is 2. Algebraic multiplicity is 2, geometric multiplicity is 2. We shall make a few time कब तक है? हो गया है. चलें इसी डिस्कशन को हम इंशाल्लाह कंटिन्यू करेंगे.